Hi everyone. So welcome to the session. Okay, somebody requesting to join. Yeah. Okay. So now we are going to discuss about you know the concept of overfitting and underfitting. Okay. This is also called as bias variance trade-off concept. Okay. So bias variance trade-off concept. This lecture, anyway, I shared you the link of machine learning university from Amazon. Okay. So this is really a wonderful site where you can visualize the things and understand the things in a better way. Okay. And this will really help you to understand the concept, what exactly happening there and why it is important, this concept, and in what way we can, solve this. Everything you will get to know. There is one more thing actually that is, math works. Math works. This particular website also will be really good for machine learning and artificial intelligence. But the only change is here they don't use Python. Instead, they use MATLAB software and MATLAB programming languages. Okay. So, like how you can do the regression and classification, everything, they will also explain. The material is also really nice. Those who are really interested into signal processing or else embedded software related things, those guys, you can focus on MATLAB or MathWorks provided documentations. This is one good source. And one more good source is Amazon or IBM or Google. Any of these tech companies, they also publish courses. For example, many times I refer Amazon, AWS, okay, space, machine learning, not certificate. If you are interested, you can do certifications also, but the materials are all open to all for learning. But if you want to do certification, yes, you have to pay for it. Machine learning on AWS, that is different. We don't want that. We want only the explanation of machine learning. Okay. So here also it is really nice if you want to go and explore generative AI and business essentials. What all topics are really essential, to learn machine learning, where you can get all the things. This is also I also reviewed. This is really nice. The topics are really nice. You can also in your free time you can go ahead and learn. Okay. So it is free. You can see enroll. You can easily free, but examination is costly. Okay. So if you are interested, you can do the dedicated course. That is also good. Or else IBM is also really nice. Or cognitive sciences is there. Cognitive. Okay. IBM machine learning. Their cognitive classes actually. Okay. Machine learning using Python. Yes. This is the one I really recommend you. This is also good. There you can see K nearest neighbors, decision tree, random forest, advantages and disadvantages, regression, model evaluation, overfitting, underfitting. See, overfitting, underfitting concept is also there. Okay. So there also you can go ahead and enroll everywhere. Enroll it is free, but only thing is certification is what costly here. Okay. And there is one more actually. Yes, this is also really nice. This is also really nice. IBM. This is from cognitive. These are from cognitive sciences. Okay, cognitive, but though cognitive, it is also supported by IBM. IBM Labs actually. Okay, and here machine learning is also really good. If you are interested, you can also enroll Coursera certifications also, or else you can even explore our AI solutions. Or there is actually one straight away course is there. Long back I referred that. It is really nice. Okay. Yeah. So there are many ways if those guys who really wanted to learn from out of the box and really wanted to focus on uh, different materials and different use cases and all, yeah, you can explore IBM or AWS, MathWorks. Okay, cognitive AI and this ML University or CS 229. Okay, CS 229 is also good. Stanford University, but it is, I think, we have to pay. I'm not very sure. This is also really good, but I'm not sure whether it is fully free or not. Hmm? Yeah, very good material also available here. Okay, already courses there, right? Yeah, this one, this type of courses. Lecture 1, you can watch, you can download. Lecture 2, PDF also available. Okay, so simply you can go ahead and but a lot of theory we have to go through, and then mathematics will be there. Really nice. These are also nice books also there. If you are interested, please let me know. I will also recommend nice books. Pattern Recognition by Rishabh. That is good. Good book. Okay. Now let us come back to this session. So now let me explain you what exactly this overfitting, underfitting, and how to achieve the optimal problem or optimal model fit, how to achieve that, why it is important in machine learning. This concept applicable to all the algorithms, not irrespective of supervised or unsupervised. It is common in machine learning, evaluation part. Okay. So first of all, so before going to underfitting or overfitting, it is important to understand what is bias and variance. Okay. The bias is a term which is there in machine learning or deep learning. Okay. Down the line, you're going to learn about this. I mean, you're going to continuously hear these terms, overfitting, underfitting in deep learning as well. So first of all, bias is the concept what we have to learn. This concept is nothing but it refers to the, it is simply, I have provided an example, simple, and so first let focus on this example so that it is really easy to understand this concept. Imagine if you are shooting the arrows at the target, archery. Okay. High bias means consistently you are missing the target in the same place. You are missing, you are not hitting the target. Instead, you are missing, and that too in the same place you are missing in the same consistently you're missing the target. Okay, so similarly if a model has high bias, the model will going to ignore the complex patterns in the data, and that will leads to the underfitting. So we do have two things: overfitting, underfitting. Underfitting causes because of bias. Okay, because of high bias. Okay, and in general bias is something like training error. Error happens with training data set. Okay, testing data set, if there is an error, that is what we in general we call it as variance in general. Okay, high bias, if we have high bias, that means it is ignoring the complex patterns, and that is going to lead to a model to go for underfitting. Underfitting means you want to learn from the data or from the textbook, but instead you did not learn some concept, you skipped some concept. For example, let me tell you a short real time example. In in graduation or post graduation, wherever you are, so you will have a textbook and you will have a notes. In the notes it is very clearly mentioned that refer to this textbook for further topics. So they will not cover, right? The lecturers will not cover because they don't have complete time to cover that concept. So they want you to refer that and then prepare for the examination. Okay, for example, the same concept, support vector machine. So I just told you to do to walk through my material and walk through my lecture, and also I told please refer from online sources, or please do refer from so and so Amazon's course or some course. But if you forgot to refer them, suddenly if I put an examination, okay, in that examination the topics came from the reference resource, which you were skipped, let us say. So that means you missed some data, important data to learn, but you learned, but you missed what is also needed. Okay. In that situation, you were underfit. That means you did not learn completely. You will not perform well, obviously. Correct? So same situation, data set also, if model, did not took consideration of all the data, instead it, if the model ignoring the complex patterns in the data, and that will lead us a model to underfit. Okay. So in ML also, if you are using linear regression, for example, the data is arranged as a curved relationship. It is not linear, let us say. It is curved. The data is, pushing you to apply a polynomial regression. Okay. But instead, if you used, if you use the linear regression, then linear regression means a straight line. So that means you're going to skip some complex patterns so that your model going to be underfit. Okay. So what is the impact of this underfit on model performance is high bias model performs poorly at the end on both the training data and testing data, because it will lack the flexibility to adopt to actual parameters. And underfitting also occurs if the model is too simple to capture the complexity of the data. Okay, remember these 2 points. Okay, what is the impact if we have underfit means underfit occurs when the model is too simple to capture the complexity of the data. One thing, and one more thing is, this is what the really important, the first line which I mentioned here. High bias model performs very poorly on the both the training data and the testing data, because it is going to lack the flexibility. Anyway, I will show you what exactly all those topics with visualization with the help of this reference. And variance means, I just told you, right, it is generally impacting on the testing side, error rate. But here variance refers to the model sensitivity with respect to the fluctuation and noise in the training data. A high variance means model becomes over complex, learning not just the true patterns but also the noise and idiosyncrasies in the data, and leading to overfitting. What is exactly this do is, for example, you know, if I ask you to learn uh, 10th grade mathematics textbook, but if you are overexcited and you skipped the 10th class main topics, instead you went to plus one, plus two textbooks, you were very excited, and then you want to know the complete ending part of that concept. Let us say trigonometry. Trigonometry is there in class 10th, and it is also going to be in plus one, plus two, even in engineering. If you're very much interested in the trigonometry topic, if you focus more into that, and if you go to the extend level of plus one, plus two, if you are not focusing on the only class 10, if you're focusing on the entire that particular topic, you are very much keen to learn, then you are going to be overfit. That is also not good, right? Because you are going to miss the real complexes of the and patterns of the data, current data. Instead, you're going to uh, train on over much. Right? That is what here it is very clearly mentioned. Learning not just the true patterns, but also the noise. That is going to be noise. Okay. And that will lead to overfit. Okay. What is going to the impact of model on model performance means, if you have a high variance, then has low training error. Okay. And because it memorizes the training data, but the high test error, I told, right, it is comes with the testing side. Okay, high test error you will get because it struggle to generalize to new data. Got it? It will really struggle to generalize the new data. Okay, this is like memorizing answers for a text, but if the test question changes, you will not able to perform well. This is the best example. Okay, memorizing the answers for the particular test. For example, if we change the values, you will not able to answer them properly. Okay, so this is what overfit. And bias variance trade-off means, the main goal of this one is we have to achieve a balance between bias and variance in order to build a model that should neither underfit nor overfit. That is what we want. That is what the goal. What is this trade-off then? Trade-off means reducing the bias that will often increases the variance. That means the seesaw, balancing the seesaw. Okay. And reducing variance may increase bias. Okay, that is the goal is to find the optimal level of complexity where the model capture the key patterns without memorizing the noise. We have to make sure that stage we have to reach. That is what the goal. And again, to overcome the okay, if we face any underfitting, then how do we overcome that? If we wanna overcome the underfitting, then this is the concept. We have to reduce the regularization. That is what I'm going to explain you. L1 and L2 penalties. Those are penalties. Okay, which is an extra parameter what we are going to add. So to the existing formulation, that is what a penalty. Simple concept it is. Okay, we're going to reduce that regularization. Remember this point. If you want to overcome the underfitting, these are the steps. Reduce the regularization. We have to train the model for longer, and we have to, in order to overcome outfit. I mean overfitting to over. Okay. Next, so if we want to do, here I just need to overcome. Yeah, this is right the one. Yes. So if we want to overcome the overfitting, high variance, then what are the steps means? First of all, we have to apply the regularization. What is the difference between the regularization in two cases means underfitting if we want to overcome, we have to reduce that factor. Here we have to apply, we have to add, understand? And then we have to go for, we can go for cross validation if we want to tune hyperparameters. And then, we can simplify the model. And these are the, and also we can even go for methods like ensembling methods like bagging and boosting. These are the ways to do to handle the underfitting and overfitting. Okay, how do we solve this? Simply, I just considered x random values and y random values. Here we can see x and y random values are there. Some 30 comma 1 random integers and into 10 and axis is equal to 0. And y is another one. Okay, so just I consider this and then I am going to plot them to understand. Blue color lines are just the data points. Okay, and I'm just fitting under fitting line that is in red color, and best fit line which is in green color, and overfitting line which is in orange color. Okay, so how do we define this? Means simply we are adding degrees. That is what. Okay, degree. Degree is equal to 5 is what? Optimal one. Degree is equal to 1 means this is underfitting one, which is in the color of red. Observe the red color. This is underfitting. The data points are like this, but we are underfit. Then best fit line, if you observe the best fit line, this is what the best fit line. And overfit line, this orange color is overfitting line. Of course, if you feel confusion, then don't worry. We have this material to understand. Okay. Here we can see what is bias and what is error from variance and error from bias. Means training and testing error. Trade-off means it is have to ability to minimize those things. It is worth taking the time to understand the concept actually. Yes, it is true. Uh, yeah. So going down, this is a data points. Let us consider these are the data points. These are the best fit line. So simple model is simple model. If we take a simple model, so this is going to the best fit line. So these are the errors, the dotted lines. I already mentioned the error. That is, the this is an error difference between the original one and the predicted one. And if I say mean square error, this is what the mean square error. Okay, this error has to be minimum, right, for the best fit line. Okay, going down. So the red color data, this blue color data is what the training data, trained training data. The training data, if I go ahead and find the best fit line and find the errors, this is the errors, mean square errors of the training data. So some random points which are there in testing, got it? These are denoted by red color, you can see. So the red color points are the real test values, but here you can see the test points and the the best fit line is far away. That is why the error from the test is high. Okay, error from the test side is high. I already mentioned you. So this is going to be bias, means it is going to be high bias. Okay, and here this situation is, you know, underfitting. Then a complex model. Let us consider one more model. So if not, this is the straight line is, if, let us say if straight line is not the best fit line, then we can go and add degrees so that we can cover this polynomial, uh, you know, polynomial way. So that is why slowly just increased the degree so that we can cover all the training points, but still the testing points are not so good with aligned with this. That is why here if you see training error is 0, means every point it fitted properly, but testing side it did not able to fit. That is why testing error is high, training error is less. Okay, training error is less, testing error is high. So this particular concept is called overfitting. Overfitting refers to the case when model is so specific on the data. Okay, let me add. Yeah, please, someone is having a doubt. No, no. Jnanesh wanted to add. Okay, fine. Okay. Remember this concept. Overfitting refers to the case when a model is so specific to the data on which it was trained on. That's it. On which it was trained on. Only it focus on the training set. It is no longer applicable to different data sets. Okay. That is why it is having high error in testing. Training side, no error, 0. So such cases is called overfitting, high complexity and overfitting. Okay. So ideally, in the general case here it is mean square error is something like can be decomposed into three components. Error due to bias, that is what bias, first factor, should be squared plus variance. Okay, due to the variance and error due to the noise. We can even skip the noise one, but of course in real time data sets are having some sort of noise will be there. So bias square plus variance, and the actual formulation is this one mathematically. Okay, see in reality how it will be is bias represents the difference between average prediction and the true value. Okay, so if we plot that, this is how it will be. Okay, so if you go ahead and see the variance, so it will be like this. But if you go ahead and see the balancing between this is what the actual best fit curve. Okay, this is what the actual best fit curve. Here we can see the balances. Error should balance with the bias and no variance. Here you can see the red color. But here if you observe error is simultaneous with variance, right? That is why it is called variance. In this situation, error is with bias curve. Are you getting my points? Error is with bias. That is why it is having bias. But here in variance, it is with variance, green color. Now the best fit line, if you see, both are all trade-off. This is the trade-off situation. Both are leveled. This is all the mathematics behind this. Okay, and this is how the trade-off will be. Like here, you can see the bias one and the variance one. Both are trade-off. Okay, and there is one regression is there that is called losses regression. Losses regression is actually, you know, here we can see the training accuracy is training error. It is not accuracy. Training error is less. Testing error is more. So what we have to do is In this algorithm particularly, we have to smoothen, we have to perfectly align the smoothen, so that these two going to be trade off. For example, if I increase this training accuracy, testing both are high. If I reduce this, this is the concept of overfitting. This is overfitting because it is not able to pick the testing points perfectly. So if I slowly maintain smoothness, one point of time it should come trade off, means almost same. We have to identify that. Smooth, somewhat both are almost same. So it is sometimes it is not possible to get the exact same value, but instead we can get the closest smooth end value. Okay, with minimal training error and minimal testing error. If training error means bias is less and variance is less, means that is what best fit line. Okay. Yeah, in K nearest neighbor already we discussed that. Yeah, that is all about the concept of, the simple. It is very simple. See, understand. Your end goal is, if you are doing a machine learning algorithm, your end goal is you have to make sure both the errors are less. Okay. If anything is altered, then you can use this concept called regularization to correct the data, to correct not the data, to correct the model by adding penalties. Okay. For example, here it is saying, okay, high variance means if you have high variance, then that is called overfitting. If you have high bias, that is called underfitting. So now it is very easy to understand, right? So remember these 2 points. High bias means underfitting. Here in this particular thing, bias means occurred with training accuracy. Here what we have, testing means high variance. Bias is less, right? Bias is absolutely zero here. But we have a lot of variance. So lot of variance means high variance means that is the concept of overfitting. Got it? If you have high bias, okay, high bias in this, both are testing accuracy is what dominating, but sometimes you feel, I mean, you will observe with your practice. Okay, so you will get the high bias, then variance, then that concept is called underfitting. Okay, then how to deal this? Okay, how to deal this? Low bias plus low variance, that is what the good generalization. I already told that you should have low bias and low variance, both should be less. That is what the bias variance trade-off best fit line formulation. Okay, let me consider a small example here. You can see, this is a small plot. Simple again, some random values of x and some random value of y. We just used, to show you. So the blue line is what training error. The orange line is what testing error. The optimal fit is what the green line. So here is what the optimal fit. Okay, where training accuracy is less and even testing accuracy is less. So both are less at that point. So we have to identify that. Okay, how to handle this underfitting then? How to handle? Okay, let us consider we have underfit. Then how to handle this? Techniques to fix underfitting are, we can increase the model complexity. That means we can use more complex models that can capture the underlying relationships better. An example of regression, for example, use polynomial regression instead of linear regression. Okay, so in case, let me take a paint. Uh, Let us say your data points are like this. Okay. So you used perfect fit line. Got it? So this is what the perfect fit line. So here lot of training error itself we got. You can see training error is lot. The data points difference is what error, right? Prediction and actual. Training error is high. Training error is high means high bias. High bias means underfit. Then what is the technique? You can use the concept of regularization so that you can increase the polynomial features to it. I already showed you how to use the polynomial features in feature engineering also. Now you can understand why it is important. Okay, now the actual concept came of polynomial regression. I mean polynomial features. So that this best fit line instead of straight line, we will add up a squaring, right? Squaring parameter so that it will slowly convert as a curve. It will be like this. It is based on the degree, how much degree you are adding. So that it will become a curve and it will now the training error will get reduced. Got it? This is one concept. Instead of straight line, we can go and experiment with polynomial regression. Next, use the decision tree. If you are using for classification, for example, if you identify the same type of issue in classification, then if you are use the decision tree and with deeper branches and increase the number of deeper branches instead of shallow trees. And then if you want to reduce and second one is reduce regularization strength. Regularization strength is simply L1 or L2 regularization, anything that we have to try reduce its strength. I will show you what is that meaning and all, no problem. But just remember these things. Okay. And how to handle the overfitting means simply the model, simplify the model, reduce the model complexity by just doing the pruning and decreasing the number of layers. Actually, in neural network, anyway, it will come later on. But here it is the best thing. Use the regularization. I already showed you the first concept. These points are actually important. To overcome underfitting, we have to reduce the regularization. To overcome the underfitting, we have to apply the regularization. These 2 points you always have to remember. Okay. So don't confuse. Let me again give you a glimpse. Then we'll ask you your feedback whether you understood or not. So let me explain you very clearly the what is this and why it is really important in machine learning means. See, bias variance trade-off. Trade-off means it's a balance between bias and variance. Why this is concept is really important means we know how to use machine learning, we know how to apply machine learning, right? So once you apply machine learning, if you get the accuracy, let us say 90% or 80%, so you also have to check with whether you got the accuracy with training data and testing data, both are almost same. Otherwise, your model did not learn perfectly. For example, out of 5 units, okay, you have to study 5 units and you have to answer 5 questions. 5 tens are 50 marks, let us say. Out of 5 units, let us consider if you miss 1 unit, okay, 4 units only you learned, or 3 units only you learned, then your accuracy will be 70% or 80%. Definitely, because you missed, you were underfit. You did not cover all the data points. That is why you are underfit. How to overcome that? Simply, you have to cover everything. You have to make sure that you have to cover everything. That is why in linear regression, if you are facing this situation, then try to go and apply uh, you know uh, this polynomial features and then polynomial regression you can go instead of linear regression. So that adding the degree will actually convert a straight line to the curved line. So that it will make sure to cover every point. Okay. So in order and also one more point you have to remember, there is a concept called regularization. There you have to reduce those parameters. Regularization means reduce them. Okay. Second, when it comes to, you know, that is what underfitting. I hope it is clear. Then overfitting means you learned concepts. It is that you learned concepts. What is exactly there in the syllabus you learned. But if you are failed to apply in real time, for example, you learned you know, uh, y is equal to mx plus c, where m is equal to 10, c is equal to 20. And you know, if any x value comes out, then y is equal to mx plus c means simply you have to replace those values and answer me the y value. For example, in the examination, real-time examination, examiner asked you with different m value with different c value. Okay, then if you failed to implement that same logic in reality, whatever you learned, that is also not meaning that you learned. For example, let me show you here. Y is equal to mx plus c. This is the formula. You prepared as m is equal to 2. This is 2. C is equal to 10 and x is equal to 4. Then you know that y is equal to simply 2 4s are 6. Sorry, 2 4s are 8 plus 10, 18. You know that this is correct. In textbook, this is what written. But in examination, examiner given m is equal to 4, x is equal to 8, and c is equal to 12. In this situation, if you failed to substitute these values here, and if you did not, I mean, you are not able, if you are not able to answer this question, what is exactly the y value after replacing these values in this expression, then that is also not meaning that you learned it. You just by hearted, and then you are not implementing the concept in reality. In overfitting, this is the situation. It only knows very well about the training data, but in real action, real times, it cannot even apply any learning concept to detect the pattern well and able to answer or able to predict the future points correctly. That is why either if your problem or machine learning is having bias, or if your problem statement or your machine learning model coming up with variance, both are not good sign of learning. Then how do we know whether our machine learning model correctly or not? Means always you have to check for what is the training accuracy and what is the testing accuracy. If both are almost same, then there is a trade-off. So both are. It is not having training accuracy high, training error high. It is not having testing error high. So it is both are almost same. Then that is what the best fit line. Got it? Okay, we know that best fit line. What if I have training accuracy more? Sorry, training accuracy less. High bias means training accuracy less, right? So because error and accuracy both are inversely proportional. Always remember, if you have less error, that means you will get more accurate model. You're going to get more accurate model. If high error is there, means you will get low accuracy in testing. Sorry, in training. You will get low training accuracy. That is nothing but underfitting. And similarly, if you're similarly, it is quite opposite in the case of overfitting. I hope it is already clear. I'm not going to tell again because you will get confused. Okay, then how to deal that? Let us come to that topic. Regularization is one concept will help us to deal that effectively. Here now, how to handle underfitting high bias means techniques I already mentioned. Reduce the regularization strength and all also covered. Now see. Now understand this concept called lasso regression and ridge regression. Lasso regression is also called as L1 regression. Wherever you see here, use L1 or L2, L1 regularization, L2. L1 is also called as lasso regression. What is will it will do? It will shrink the coefficients to zero. What are meant by coefficients? Beta 1, beta 2, beta 3, those are there, na? Y is equal to mx plus c. In that formulation, y is equal to mx plus c, or else beta naught plus, we learned, right? Beta naught plus beta 1 x1 plus beta 2 x2 upsilon beta n xn. This beta 1, beta 2, beta 3, these are all called as coefficients. So L1 regression, the concept is it will focus on to shrinking, it will focus on the shrinking sum of its coefficients to zero. Okay, we will reduce the impact of the coefficients. So that is what L1 regularization do. L2 regularization is also called as ridge regression. What it will do is it will reduce the magnitude of all the coefficients. Every coefficient will have magnitude and direction, right? So it will reduce the magnitudes of those coefficients. Okay, L2 regularization, that is what it do. If you combine both L1 plus L2, then that is called elastic. Okay, that is called elastic regularization. Okay, yeah, fine. Let us understand L1. L1 means I already told it will shrink some of its coefficients to zero. Okay, so what is the mathematical formula is loss is equal to MSC. MSC means you know, right? Mean square error. That means the difference between, okay, the difference between the actual point minus the predicted value. I already told this concept in linear regression. Please refer that. So there we discussed about, yeah, Prajwal, what is your doubt? Come on.
You are recording this session, right, Yashwant?
Yes, yes, yes. I am recording this
Yeah.
session.
So I'm having headache and I'm not be
Aha.
able to continue the training. I'm
Okay.
planning to
Because of
leave.
this session, you are having headache, or is there any other?
No, no, I didn't get proper sleep last night.
Of course, this
I'm
concept
sure
is
it's not this.
yeah, because this is somewhat different from what you learned earlier. Earlier, so far you were not focused. Yes, sure, Prajwal, you can drop off. You can have this session later on. That is fine. Ah, okay, guys. Let me tell you one thing clearly. So please give me a second. I will come up with pen and paper. I will connect my pen and paper. I will literally wanted to show you. I know that this concept actually makes you difficult to understand. So now what I need is a responses from your side one by one or else anyone. So tell me correctly. As of now, the regularization concept, especially this underfitting and overfitting, anybody confused or else not? If confused means I would like to show you with real quick way of example. If not means I will continue. I need your responses. Maria, confused or most of
It's
somebody in
better if you show on paper.
yeah, sure.
I
Here
mean,
you
it
can
will
see.
give more clarity. I
Yeah,
understand it, but it's
definitely.
a little different. Yeah.
Definitely. See, focus on the screen. It is kind of confusing, but don't confuse because this is such a concept like that. Okay. So our I'm considering example of regression. Okay, first let me explain in regression. Classification also it is the same concept. Here regression means we are going to find the best fit line where we are going to classify the class correctly in classification, right? So in regression, if you understand in regression, same concept works, same way works in classification for sure. But here it is very important to understand the regression. Let us say these are the points of X and Y. These are input features. This is output feature. Now my goal is, you know, now my goal is to find the best fit line. Okay. So if I come up with this is the best fit line. Let us say this equation is phi is equal to beta naught plus beta 1 x1 plus beta 2 x2 up so on. How many values we have? For example, 1, 2, 3, 4, 5. So 5 betas will come. 5 x values will come. And there is one y-intercept. If y-intercept is 0 means, yes, here there is no y-intercept, right? So that is why beta naught will be 0. Got it? So this is the final equation of this line. Okay, you know how to use machine learning to fit this line. But after that, model evaluation is also there, right? Then only machine learning completed. Otherwise, it is not machine learning. Only you build the model, that's it. But you also have to go for model evaluation. How to do that model evaluation perfectly means One regression means matrix is important. Every algorithm having its own matrix. For example, regression have regression matrix. Classification algorithms follows classification matrix. Regression matrix, one of the important matrix is error. First matrix is error. From error only all the matrices were derived. Without calculation of error, there is no other matrix. Okay, if you know how to calculate error, then you will get the mean. That is what mean square error. Sorry, mean absolute error first. And then mean square error. Then root mean square error. Then R square. These are all came from error. What is this error? Simply your actual y actual minus y predicted. What is meant by y actual? The point which you have plotted actually according to the data set, right? This is what my x1 and this is what my y1, right? This is actual data and this is what my y2 and x2, correct? This is what my actual point according to the data set. This is what my data set x, y, blah blah blah. So according to this x and y, this is the point. But my model, when I used machine learning, the same concept, I find out all the beta ones, all beta, all coefficients, all y-intercept, and then I just used my x values and replaced that. This is what the best fit line I got. But in reality, what is the error means? Y actual point, let us say the error, this is actually it is 5. But what we predicted means the line, the point which x1 is same. Remember, x1 is same. Okay, prediction means always the point which y value which is on the line with that respect to x. This is what the predicted value. Got it? So predicted value, let us say it is 4. Actually is 5, but we got it as 4. Then error is 1. Similarly, all the errors means that is why these dotted lines are represented that the difference between the actual, this is actual, and this is predicted. These dotted lines defines like that. Okay. So if you calculate all such errors, that is what all errors. And if you do the mean, mean means you know right sum of all the errors divided by total. That is what mean absolute error. If you square them, mean square error. That means 5 minus 4 whole square. That means 1 square 1. Similarly, 6 minus 5 whole square once. Okay, all squares. If you do mean, that is what mean square error. This is we already learned. So this mean square error should be low. If we get the error low, that means this, then only the model had the best fit line. This is what the training data. This all the training data. Training data means whatever we had already trained, we used for training. If this is having error high, okay, if you are having an error in training itself, and that too high, error high means accuracy low, isn't it? Because we are estimating that error should low, then only accuracy high. But here we are getting error high, that means accuracy low. Error high means high bias. Bias is nothing but, remember, bias is always focused on training data. If you are getting high error in training, that is called as you are having high bias. If your high bias means that concept is called underfitting. Right? This line did not fit properly. That is why it is called as underfitting. Then how to deal with regularization, or else you can use this concept of, let me take orange color. Instead of linear regression, if you go for polynomial regression, then your might be you will get like this curve. Instead of straight line, we will go for curve. Then somewhat error can be reduced, right? The distance between these 2 points is lesser than previous straight line and this, correct? So that is why if you are having high bias, that means low accuracy in training. That is called underfitting. This underfitting, one thing you can immediately correct is do the hyperparameters, add the polynomial features, and then train on them polynomial features, so that instead of straight line you will get the curve. At least some points are very clear. I mean, some points are very near the actual data and predicted data. Somewhat error can be reduced so that accuracy can be improved. This is one technique. Or else second technique is using regularization. The topic is regularization. There are three types of regularization: L1, L2, L1 plus L2. Combination of these two. What is L1? I told, right? So let me go ahead and show you. L1 means lasso regression. Okay, that is called L1. Regularization is also called as lasso regression. Similarly, what is L2? L2 means ridge regression. Okay, L2 means ridge regression. Then what is this combination of L1 plus L2? This is called elastic regression. Got it? So in underfitting, we are now discussing only underfitting. In underfitting, what is happening is, if we use L1 regression, that means lasso regression, then we are going to use these coefficients are there na, beta 1, beta 2, beta 3, beta 4, beta 5, beta 6. 6 points are these coefficients. Some of these coefficients we will reduce to 0. Got it? Then we can improve this. Got it? That is the how mathematically derived. If you ask like how it will be possible, means you can refer the mathematics and you can refer the proofs. It is already defined by the mathematicians. They already performed a lot of experiments and they published the papers. They finally proved that L1 regression is actually will help to overcome or to solve underfitting problems. Now underfitting is clear. The concept with underfitting is clear. Now please respond. Is it clear? Okay, Samreen said yes.
Yes, yes, Ashwin.
Now it is clear, right? Very much.
Yes.
Okay, fine. So that's why if theory important and mathematics is important and coding also important in machine learning, especially if we have any one thing, like if we have theory but no mathematics but no programming, definitely that concept we will not going to remember for longer time. Okay, that's why learn these three things in your entire machine learning journey and deep learning journey. Okay, now we can focus on remaining thing, overfitting. Now what is overfitting means, if we have points like this here, 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 and here. What is happening? How many taken? I took 1, 3, 6, 6.7 points I took. So generally, this is if I plot like this is what the best fit line. But in overfitting, what will happen is it will go and touch every point. It will try to cover every point. Then what is the problem here? Because every point it is covering, then what is the problem here is training data, it is fine. Training data, it is very good. So we will get, if you calculate the error means I just told you the difference between the predicted and the actual. Okay, if you calculate the error, training error, especially training error, it is far less, so close to 0. Okay, accuracy, it will very good. Means less error means you will get around 98, 97 or above 90, greater than or equal to 90% accuracy are good. But reality comes to the real data, test data. This is test data. This is test data. This is test point. 4 test points are there because 80% goes to training, 20% goes to testing, right? Now, if you go ahead and calculate the error means this is the predicted one. This is what the actual one. This is predicted one and this is actual. predicted, actual, predicted and actual. And now what we are having is testing error, testing side error. It is high. That is called high variance in what is this concept? Underfitting. Sorry, overfitting. Overfitting. Here we will have this the high variance and obviously accuracy. Testing accuracy will be less. Sorry, lesser than means this one. Very less. If you have a situation, training accuracy is very good, greater than, and testing accuracy is very less, then this concept is called overfitting. Because training accuracy is good means less error. Remember that concept, don't confuse. Training accuracy greater means less error in training, but more error in testing. That is why testing accuracy will always be less in underfitting situation. So then how to deal this? Under underfitting means we will go to L2 regularization, that is called ridge regression. In this concept, magnitudes will be there, right? Beta 1, beta 2, beta 3. That magnitude we will lower then. We will reduce that. So then this is what about underfitting. Then what is the another concept like best fit line? So far you understand what is all the things, but what is exactly this one? Best fit line is simply so these are the points. Let us say it will come up with a like this. It will have training accuracy, testing accuracy, both are almost equal. Almost equal. Errors also both are. It will not have high error in training. It will not have high error in variance. Okay, I mean testing. So you will have a balance. That is why it is called trade-off. If you put like this, seesaw. Okay, like this. One person is here, another person is here. Seesaw, balance. If you like this a situation or this one, both are not good in model evaluation. Model evaluation. So you have to come up with a best fit line. Then how to deal case one, underfitting, case two, overfitting means with the help of regularization. Then now understand this concept called regularization. Now see the formulation. What we are going to do in lasso regression, also called as L1 regularization. Simply loss formula you know already, right? Loss formula you already know. MSC, mean square error, I just told. We are adding an extra penalty. We are adding an extra penalty to it. That is what lambda. Lambda is called here regularization parameter, and that has a control. Okay, that has the controls, the strength of the penalty. Okay, so this is how lasso regression works. And ridge regression means this is the formula. Here we will add a square. That is the only difference between these two. Here modulus of this beta I. Okay, beta means coefficients. You know, right? Coefficients. Here we will add a square of those coefficients. That is what the extra penalty that we are adding. And here to reduce, it reduces the overfitting by just penalizing the large coefficients which are there in the large coefficients, but does not shrink all the coefficients to zero, but instead it will penalize the large coefficients. But here it will shrink some of its coefficients to zero. Got it? This is the way how to come with a best fit line, though we have either underfitting or overfitting situation. Or programmatically, see, this is underfitting situation because here if you see underfitting model, score means accuracy. It is having high score. Okay, underfitting. Mean square error. It is having 81% error. Here, the data set has some noise fitting the linear regression might lead to underfitting. So to reduce that, we are going to add with a R2, sorry, R square. But it is indicating by R square and high mean square error. Okay, low R square, remember this point. Low R square and high mean square error if you have, that is what the situation of, indication of underfitting. And you can use this way. I already told polynomial regression we can go, and degree is equal to 3. You just need to alter the degree so that you will get the best fit lines. Then you can see R square and mean square error. And here it got, you know, it is kind of fixing the underfitting. And then it is concept of having overfitting. It is trying to fit all the points. Then what we are going to do is we are just adding ridge regression. Okay, sorry, lasso regression. Just changing the alpha values and iter value. These two are the hyperparameters. These two are the hyperparameters. As you change the alpha value, you will get change in the best fit line. Okay, that is important. So this is the way how we can deal, overfitting and underfitting situation. Basically, ridge regression, L2 regression, it will smooth the curve, polynomial curve, okay, and reduce overfitting by shrinking large coefficients. L1 regression, it will shrink so some of its coefficients is directly zero, and it will perform feature selection and reduce model complexity. Okay, so that is all about bias variance trade-off. Now is it clear? Now have you understand the concept of bias and variance and trade-off? Now is it somewhat clear?